Have you ever wondered how energy moves and changes in a system? Welcome to the intriguing realm of thermodynamics, a branch of physics that answers just that. Thermodynamics investigates the principles of energy transfer and transformation. And it's not just limited to physics. It's a fundamental cornerstone in a variety of fields, from chemistry and engineering to cosmology. Now you might be thinking, what makes thermodynamics tick? Well, there are 4 laws that govern it, each one as crucial as the other. They are the Zeroth, First, Second, and Third Laws of Thermodynamics. These laws, as simple or complex as they may sound, are the guiding principles that explain the behavior of energy in any system. They allow us to understand why ice melts, why engines run, and even why the universe is the way it is. Intrigued? Then buckle up. Let's delve into the fascinating world of thermodynamics. Starting with the Zeroth Law of Thermodynamics, let's dive into this intriguingly named law. Despite its name, the Zeroth Law was the last one to be named, but it's so fundamental that scientists felt it deserved a place at the start of the queue. At its core, the Zeroth Law of Thermodynamics is all about temperature and thermal equilibrium. Picture this. You have 3 cups of coffee. The first cup is piping hot, the second is lukewarm, and the third is ice cold. If you were to pour the hot coffee into the lukewarm cup, the combined coffee would reach a middle ground of temperature, neither too hot nor too cold. This is what we call thermal equilibrium. Now, if you were to pour the lukewarm coffee into the ice-cold cup, again, the mixture would find a new middle ground. The temperature in the cup would be cooler than the lukewarm coffee, but warmer than the ice-cold coffee. Once again, thermal equilibrium is achieved. The Zeroth Law of Thermodynamics states that if 2 systems, in our case the cups of coffee, are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. In simpler terms, if our hot coffee and our ice-cold coffee are both in thermal equilibrium with the lukewarm coffee, then they must also be in thermal equilibrium with each other. This law is the cornerstone of temperature measurement. It's why we can use thermometers to measure temperature. When we put a thermometer in a cup of coffee, the thermometer and the coffee come into thermal equilibrium. The thermometer scale then indicates the temperature of the coffee. So the Zeroth Law, as simple as it seems, is incredibly important. It's the foundation for the concept of temperature, and it allows us to measure heat and cold in a consistent manner across different systems. So the Zeroth Law essentially allows us to measure temperature and use it as a physical property. Moving on to the First Law of Thermodynamics, also known as the Law of Energy Conservation. This fundamental principle is all about balance. It tells us that in any closed system, the total energy remains constant. Now, this doesn't mean that energy stays put. Far from it. Energy can and does change forms, but the total amount of energy always stays the same. Let's put this into a mathematical perspective. The first law of thermodynamics is often expressed as delta U equals Q minus W. Here, delta U represents the change in internal energy of a system. Q is the heat added to the system, and W is the work done by the system. If we add heat to a system or do work on it, we increase its internal energy. Conversely, if the system does work on its surroundings or loses heat, its internal energy decreases. To elucidate, think of a steam engine. In a steam engine, heat from burning coal is transferred to water, turning it into steam. This steam then does work by moving the pistons. Here, heat energy is converted into mechanical energy. The total energy, however, remains constant. Or consider a more day-to-day example, a rechargeable battery. When you charge your battery, electrical energy is converted into chemical energy, which is stored in the battery. Later on, this stored chemical energy is transformed back into electrical energy to power your device. But again, the total energy stays the same, it's just changing forms. So, whether we're talking about steam engines, rechargeable batteries, or any other system, the first law of thermodynamics is always at play. It's a constant reminder that while energy can change its mask, it can't leave the masquerade. It may dance around, changing from one form to another, but it never exits the ballroom. Hence, the first law affirms that energy can neither be created nor destroyed, but can only change forms. Next up is the second law of thermodynamics, which brings us to the fascinating concept of entropy. Entropy is essentially a measure of disorder or randomness in a system. It's like the messiness of your bedroom. The more disordered it is, the higher the entropy. The second law of thermodynamics states that the total entropy of an isolated system can never decrease over time. This might sound a bit abstract, so let's break it down. Picture a sandcastle on a beach. Over time, wind and waves will gradually erode the sandcastle, turning it back into a flat, uniform beach. The sandcastle represents order, while the flat beach represents disorder. The process of the sandcastle eroding is a natural one, moving from a state of order to disorder, thus increasing entropy. Now, let's look at the mathematical expression of the second law. It's elegantly simple. The change in entropy, represented as delta S, is always greater than or equal to 0. This means that entropy can either increase or remain the same, but it can never decrease. But why does this matter? Why should we care about entropy? Well, the second law of thermodynamics has profound implications for everything from how your refrigerator works to the eventual fate of the universe. It tells us, for instance, that energy naturally spreads out if not confined. This is why hot coffee cools down if left on a counter. The thermal energy in the coffee disperses into the surrounding air, increasing the overall entropy of the coffee air system. The second law also tells us that we can't have a perpetual motion machine, a machine that can do work indefinitely without an energy source, because that would violate the principle of increasing entropy. So the second law of thermodynamics is about much more than just disorder. It's a fundamental principle that governs the natural flow of energy in the universe. Therefore, the second law implies that natural processes tend to move towards a state of disorder or equilibrium. Finally, we come to the third law of thermodynamics. This law introduces us to a concept that's as intriguing as it is definitive. It revolves around the idea of absolute zero, a theoretical state at which a system has reached its minimum possible energy and therefore its minimum possible entropy. The third law of thermodynamics formally states that as the temperature of a system approaches absolute zero, the entropy of a perfect crystal approaches a constant minimum. In simpler terms, it tells us that a system's disorder or entropy becomes minimal at absolute zero. Now you might be wondering, why a perfect crystal? Well, in a perfect crystal, each atom is exactly where it should be. There's no randomness, no disorder. Hence, a perfect crystal at absolute zero represents an ideal state of minimal entropy. But here's the catch. The law also implies that it's impossible to reach absolute zero in a finite number of steps. In practical terms, this means that no matter how much we cool a system, we can never quite get it to absolute zero. It's a bit like trying to reach the horizon. No matter how far you go, it always seems to be a bit further away. Mathematically, this law is expressed as the limit as T, the temperature of the system, approaches zero, the entropy S equals a constant S naught. That's a fancy way of saying that as we lower the temperature towards absolute zero, the entropy approaches a constant minimum value. The third law of thermodynamics may seem a little abstract, but it's fundamental to our understanding of the physical world. It governs how we can manipulate energy and matter at extremely low temperatures and has implications for fields as diverse as quantum physics and cryogenics.